All right, hello class. This is Dr. Flood, and we are going to hop into chapter 6 in your statistics course. All right, let me set everything up so that you can see my screen. One second. All right, so you should now be able to see my screen. Give me 1 second. I have to do something on some more tech stuff. Okay, so this chapter is going to be on probability. This is a very crucial chapter because it connects, again, the other chapters that we're going to go and learn about when it comes to more inferential statistics. So pay close attention. And so the learning outcomes for this chapter is going to be to understand the definition of probability, explain some of the assumptions of what is called independent random sampling, or just random sampling, how to use the unit normal table, something that we're going to be using for the next couple of chapters, and how to use the unit normal table to find scores for given proportions, and how to find percentiles and percentile ranks in normal distributions. So the tools that you'll need in order to be successful in this particular chapter is you're going to have to be comfortable with the proportions that you went over in the math review in the Appendix A, right? You're also going to need to be pretty comfortable with the fractions, decimals, and percentages, and how to convert each of these into each one, and basic algebra, as well as the z-scores that we reviewed in Chapter 5. So, an introduction to probability. So, like I've said in other lectures, research begins with a question about an entire population, all right? But actual research, what we actually do is mostly we're going to use a sample, right? A smaller subset of the larger population. And inferential statistics, the root word meaning infer, right, or to assume, is going to help us. We're going to use the sample data to answer questions about the population. And we're going to do that through using inferential statistics. And so relationships between samples and populations are going to be defined in terms of probability. And so let's talk more about that. So this is just a graphical representation of what I said. So, right, so you have a population, and then through probability, you have a sample, right? And then we take the sample, we do some kind of research design and utilize kind of inferential statistics, and then we generalize about the population from the results of our sample. All right, so again, probability is used to predict the type of samples that are likely to be obtained from a population. Thus, probability establishes sort of a connection between samples and populations, and inferential statistics rely on this connection when they use sample data as the basis for making conclusions about a particular population. So what is the definition, or how are we defining probability? All right. So probability is when several outcomes are possible, right? The probability of any specific outcome is going to be a fraction or a proportion of all of the possible outcomes. So the way we write this in mathematical or statistical notation is that, hey, we have the probability of A, right? And probability of A is going to be made up of a fraction, right? And it's the number of outcomes that are classified as A over the total number of possible outcomes. All right, and then you could take that fraction and you could rewrite it as a proportion, or you can turn it into a percentage or a decimal. And now we're going to work on some examples of this and we'll show you. So the notation for probability, or the symbol, is an italicized p, lowercase p. All right, that's going to be very important because that probability is going to stick around with us through the entire course. So that p stands for probability. All right, and again, probability of some specific event is specified by the notation p, and in parentheses, the actual event. All right, so the probability of drawing a red ace from a standard deck of playing cards could be symbolized as the probability, or P, and in parentheses, red ace. And our probabilities are always proportions, all right? So the probability of getting a red ace in a deck of cards, so a deck of cards has 52 cards, so 52 is a number of total possible outcomes. And the numerator, right, in the probability is going to be the number of outcomes classified as that particular event, right? So how many red aces are in a deck of cards, right? A standard deck of cards. Well, there's two. There is the ace of hearts, and then there's the ace of diamonds, right? So that means it would be 2 out of 52. That is a probability. Stated as a proportion or a decimal, it's going to be 2 divided into 52, which gives us 0.03846. And if we just state it as a proportion, it would be the proportion is 2 red aces out of 52 cards. So let's do some more examples with this. Let's say that we wanted to know the probability of getting a spade in a deck of cards, right? So again, in order to get a probability, we have a numerator and you have a denominator. The denominator is going to be the total number of possible outcomes. So if you're using a standard deck of cards, there are 52 possible outcomes, all right? Now, that goes into the denominator. Into the numerator goes the number of outcomes classified as that particular event, a spade, right? Well, in a standard deck of cards, there are 13 spade cards, right? And so it would be 13 over 52, which if we simplify and reduce to the lowest common denominator, it would be 1/4. So 1/4 of the deck, right, is made up of spades, all right? Let's say we are flipping a coin, tossing a coin, right? So in the denominator is going to be, again, the total number of possible outcomes. There are 2 outcomes when you flip a coin, either you get heads or tails. And so this right here is asking us, what is the probability of tossing a coin and getting heads? Heads is going to be the event, all right? Well, there are only 2 options, and one option is heads. So that is 1 out of 2, or 0.50 as far as a decimal, and 1 out of 2 expressed as a proportion, or 50% expressed as a percentage. 50%. Okay, so let's continue. So like I was kind of alluding to before, let's say the probability of something is 1/4. Well, Expressed as a decimal, it would be 1 divided by 4, which would give us 0.25. And expressed as a percentage, we would just move the decimal point 2 places over to the right, right? Or which is saying that we're multiplying it by 100, and that would give us 25%. Same with this. So let's say the probability of any of some kind of outcome is 1 out of 2. Well, 1 divided by 2 gives us 0.50. So that's equivalent expressed as a decimal. And if you wanted to know what that is as far as a percentage, we would just multiply 0.50 by 100, or just move the decimal point 2 places over to the right. And that gives us 50%. All right. So a percentage, is going to add up to 100. All right. The decimal is going to add up to 1. The fraction is going to add up to 1 if we add up all of these particular events, these possible events. So the total outcome is going to be for a fraction. Total possible outcomes is going to be 1, right? For a fraction, it's going to be 1 for a decimal, and it's going to be 100% for a percentage. All right, so that brings us to an interesting point, right? What if we're trying to find a proportion or a probability, and the event is the probability of getting black, something that's black, right? All right, but in the total possible number of outcomes, there are 10, and there is no possible outcome that is the event of getting something that is black. All right, so that would be 0 out of 10, which makes the probability 0. All right, so this was the example. Black was a black marble, right? So there are 10 white marbles. And what is the probability of getting a black marble when all of the possible outcomes are 10 white marbles? Well, it's 0 out of 10, which equals 0. On the other hand, what is the probability of selecting a white marble, right? Well, there are 10 possible outcomes, and the probability of this selecting a white marble is 10. Right? So 10 out of 10 gives us 1, right? And so if we were to express that in a percentage, that would be 100%. 100%. All right. Okay. So when we are setting up research studies, all right, we are going to use something called a random sample. All right, and a random sample is a sample produced by a process that's going to assure us of a couple of things. All right, one is that if we say we're using a random sample, that means that each individual in the population has an equal chance of being selected. All right, so everybody in our entire population has the same exact chance of being selected to participate in our study. And additionally, the probability of being selected is going to stay constant from one selection to the next when more than one individual is selected. And this requires what is called sampling with replacement. All right, sampling with replacement. So random sampling, right, again, is a process or procedure used to draw samples, right? So the previous slide was a random sample. Now we're doing the actual action or the procedure called random sampling. And it is required, for our definition of probability to be accurate. So we normally would call it independent random sampling, but we normally just leave it out and just call it random sampling. So probability and frequency distributions, right? So probability usually involves a population of scores that can be displayed in a frequency distribution graph, something that we went over a couple of weeks ago, right? And different proportions of the graph, they're going to represent proportions of the population. And again, I want to stress proportions and probabilities are equivalent. So a particular proportion of the graph corresponds to a particular probability in the population. So this is, a modified block histogram that we went over in chapter 2, right? And the scores in this, right? There are 10 scores, so it's a population of scores, n equals 10, right? And the scores are 1, 1, 2, 3, 3, 4, 4, 5, and 6, right? These are the list of scores, right? In this particular population of scores, right? So we put this into a modified block histogram, right? There's, two ones. So we have 2 ones here. There's 1, 2. There are 3 2s, 1, 2. There are 3 4s. I should put it right here. 3 4s. So 1, 2, 3 blocks. There's 1 5 and 1 6. All right. So if I were to ask, what is the probability of getting a score that is greater than 4? Well, if I was asking that question, this is how the notation would look. P for probability, right? And then we would put parentheses, right, for the event, right? And the event in this case is the probability of getting a score identified as X, a score that is greater than 4. Probability of a score that is greater than 4. So that's how the notation would look, right? So the probability of that, right, would be simply, if we had this in front of us, would simply be to look at all the scores that are greater than 4. Well, we have 2 scores that are greater than 4, right? It's 5 and 6. So we have two scores greater than 4. All right. So how do we write that in notation, right? Well, what are the total possible number of outcomes? Because that would make up the denominator. The total possible number of outcomes is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 is in the denominator, right? So that's the total possible number of outcomes. There are 10 total possible outcomes. And what are the total outcomes of the event? That being a score that's greater than 4. Well, that is 1, 2. So that is probability equals 2 over 10. Or if said as a proportion, the proportion is 2 out of 10. Or if we wanted to say it as a percentage, it would be 20%. If we were saying it as a decimal, it would be 0.20. Those are all equivalent. All right. So that's one example. Let's take this same example, right? And let's say, what is the probability, right? So the probability of getting a score, so X of getting a score that is less than 5. All right, well, that's going to equal, right? In the denominator, the total possible number of outcomes is 10, right? Still 10. And scores that are less than 5, we can count this, right? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 scores that are less than 5. So the probability of getting a score that is less than 5 is 8 out of 10, which equals 0.80, right? Which also equals 80%. 80%. All right. Or if we were to express it as a proportion, it'd be the proportion is 8 out of 10. Okay. Let me erase this stuff. Give me a second. All right. So let's do a learning check where we kind of go over some more of these problems, right? So a survey of the students in a psychology class revealed that there were 19 females and 8 males. Of the 19 females, only 4 had no brothers or sisters. And 3 of the males were also the only child in the household. If a student is randomly selected from this class, randomly selected, what is the probability of obtaining a male, right? So written in notation, right? The probability of obtaining a male is P male, right? Equals probability of obtaining a male, right? Out of this entire class. Well, the denominator is going to be the total number of possible outcomes. So how many total possible outcomes are there? Well, there's 19 females and 8 males, right? So 19 plus 8, right? 19 plus 8 gives us, oh, I'll put a 10 here. I'm sorry. 19 plus 8 gives us 27. So the number of possible outcomes, so the total number of students, is 27, 19 females and 8 males. Well, out of those 27 students, how many are male? Well, there are 8 males. So that would be 8 out of 27. All right. So that is the probability of obtaining a male, 8 out of 27, or 8 over 27. All right, so question B, what is the probability, right, of selecting a student who has at least one brother or sister, right? So for that one, we won't write out the entire thing, right? But the P is going to equal, right, the total number of possible outcomes. So that's the total number of students. Well, that's going to be 27 still. All right, and the probability of having at least one brother or sister, right? So we know that of the 19 females, only 4 had no brothers or sisters, right? Only 4 had no brothers or sisters. So 19 minus 4, right, would give us what, 15? So 15 females do have at least one brother or sister, right? And 3 of the males were also the only child in the household. So there are 8 males total. 3 of them are only children. So that makes there's 5 males, right, who have at least one brother or sister. So 15 plus 5 gives us 20. So the probability of selecting a student who has at least one brother or sister is 20 out of 27, right? 20 out of 27. All right, so what is the probability, going to 1C, of selecting a female who has no siblings? Well, the total number of possible outcomes hasn't changed. There's 27 students. The probability of selecting a female who has no siblings, right? Well, there's 19 females, and only 4 of them had no brothers or sisters, right? So that would be 4 over 27, all right? So the probability of selecting a female who has no siblings is 4 out of 27. 4 over 27, all right, is that probability. All right, so in this one, a jar contains 10 red marbles and 30 blue marbles. If you randomly select one marble from the jar, what is the probability of obtaining a red marble? Well, so this one would be notated P equals, P is red marble. That is the event, right? Marble. Probability of obtaining a red marble. Well, first we need to know the total number of possible outcomes. That's going to be in the denominator, right? It's going to be in the denominator. And the total number of possible outcomes, there's 10 red marbles and there's 30 blue marbles. So the total number of possible outcomes is 40. All right, it's 40. And so it's asked, what is the probability of selecting a red marble out of those 40? Well, there are 10 red marbles. So the probability of selecting a red marble is 10 out of 40, right? If we simplify that, that would be 1/4, or expressed as a decimal, 0.25, or if we were expressing it as a percentage, 25%. All right. Okay. Now, this one's going to be a little bit more complicated, right? If you take a random sample of 3 marbles from the jar, and the first 2 marbles are both blue, what is the probability that the third marble will be red? So remember, we're taking a random sample, right? So let's go over what that random sample means. Let's go back to that. All right. So a random sample means that each individual has an equal chance of being selected. And the probability of being selected stays constant from one selection to the next. And this requires what is called sampling with replacement. So sampling with replacement means, hey, if I get a sample, right? If I'm taking a sample and I take one person out of the population and put it into my sample, right? I'm going to replace that person. I'm going to put that person back into the population with the idea that they could be chosen again, right? Now, if we choose them again, we wouldn't put them in our sample twice, but by taking them out and putting them back into the population, our probability is going to remain constant. It's going to remain constant, which satisfies this definition of a random sample. It also satisfies the idea that each individual in the population has an equal chance of being selected. All right. So a simple simple question for this, or an example of this. Let's say there are 10 people in my population, right? And I want to take a sample of one person, right? So if I took that one person out, right, and I did not sample with replacement, if I wanted to go back in and select another person for my sample, right? Well, if I take the first person out, right, the probability of that person being selected is 1 out of 10, right? But now if I wanted to select another person and I did not sample with replacement, meaning I did not put that person that I selected first back into the population with the option of being chosen again, right? So if I didn't do that, didn't do sampling with replacement, well, then what's going to happen is that when I go to pick the second person for my sample, well, now the probability of selecting that person is going to be 9, right? That's the total number of possible outcomes, right? And it's 1 out of 9. Well, 1 out of 9 does not equal 1 over 10, right? That is a different proportion, all right? So we have violated the random sampling process. Each individual in the population has an equal chance of being selected. Well, they don't, right? In this one, it was 1 out of 10, and this one is 1 out of 9. And the second part of this is the probability of being selected stays constant. Well, this is not constant. The first one was 1 out of 10. The second one was 1 out of 9. So that is why we do what is called sampling with replacement. We take that person that we chose first and we put them back into the population with the idea that they could be chosen again. All right, so let's go back to that question. Okay. So now, if you take a random sample of 3 marbles from a jar and the first 2 marbles are both blue, what is the probability that the third marble will be red? Well, if we're random sampling, we are using sampling with replacement. So what are the total number of possible outcomes? Total number of possible outcomes is still 40. And if we are doing sampling with replacement, that means that when we took those 2 marbles, all right, those first 2 marbles that are both blue out of the jar, right, we put them back into the jar so that our probabilities can stay constant. So the probability that the third marble will be red is going to be 10. So it's going to be 10 out of 40 because we are doing sampling with replacement. Sampling with replacement. So on to number 3. Suppose that you are going to select a random sample from the distribution that we looked at with the modified block histogram in 6.2. Find the following probabilities. All right, so let's go to that. All right, let's see. Give me a second. So we did, well, no, let's see. Give me a second. Okay. So the first one is, hey, what is the probability of getting a score that is greater than 2? Right? Well, the total number of possible outcomes is still 10. And the probability of getting a score that is greater than 2, right, is all of this right here. So that's 1, 2, 3, 4, 5, 6, 7, right? That's going to be 7 out of 10. The second question asks, what is the probability of getting a score that is greater than 5? Well, let's see. It's greater than 5, right? Well, the total number of possible outcomes hasn't changed, so that's still 10. And there's only one block that is greater than 5, right? So that's 1 out of 10. So, or that's, 0.10 or 10%. This one is 0.70 or 70%. All right. Okay, and let's see. The third one asks, what is the probability, so P, and then in parentheses, the event, of getting a score that is less than 3, right? Well, the total number of possible outcomes, again, has not changed. So that is still going to be 10. There are 10 total possible outcomes. How many out of those outcomes, how many of them are less than 3, right? So there's 1, 2, 3. So that would be 3 out of 10, or 30%. All right, 30%. Okay. And so that's how you would do those probability questions. Okay. Yeah, let's get rid of that. All right, and here are the answers to the questions. We'll skip these for now. Oh, let's see this. All right, so this one asks, decide if each of the following statements are true or false. So choosing random individuals who walk by you yields a random sample. Well, that's going to be false, right? And the reason why it's false is because not all individuals walk by. So not all of the people or the population have an equal chance of being selected for the sample. All right. It sounds like a random sampling, but it's not. It doesn't satisfy those two parts, right? Everyone has to have an equal chance of being selected. All right. They do not. Second question. What is the probability? The probability predicts what kind of population is likely to be obtained. That too is going to be false. The population is already given, right? Population is already given. The thing that probability does is it's going to help us to predict what a sample is likely to be like. All right, and here is the answers. All right, so probability and the normal distribution. So the normal distribution is a common shape. We've been dealing with it for the last couple of weeks, right? That is this bell curve thing right here, all right? It is symmetrical. Remember that if you put a line through the vertical line through it, it can fold onto itself, right? The highest frequency of scores are going to be in the middle, right? Remember, this is a relative frequency, right? So the frequency is going up, right? From 0, let's say to 10, right? And so the highest, the scores that are the most frequent, right, are in the middle, right? Because these have the highest amount of frequency, right? As you go further and further away from the middle, the frequency of those particular scores become less and less, right? These are less frequent, all right? And so this can be described by the proportions of area contained in each section of a normal distribution. And z-scores are going to be used to identify those particular sections. So this is what it looks like, So here we have a normal distribution, and it's a standardized distribution, right? So in a standardized distribution using z-scores, the mean is 0, right? Mean is 0, and we're going up by standard deviations of 1. So 1 standard deviation above the mean is +1, 2 standard deviations above the mean is +2, and going the other way, 1 standard deviation below the mean is -1, 2 standard deviations below the mean is -2. All right. Now, if we wanted to know what is the proportion of scores that are between the mean and 1 standard deviation above the mean, well, that is going to be 34.13%. If we wanted to know, hey, what is the percentage of scores between 1 standard deviation above the mean and 2? Well, that's this right here. So that's going to be 13.59%. If we ask the question, what is the percentage or the proportion of scores that are 2 standard deviations or more above the mean? Well, that is this right here. And that's going to be 2.28%, right? Now remember, this distribution is symmetrical. So whatever is happening on this side is also happening on this side. So this is also 34.13%. This right here is also 13.59%. And this right here is also 2.28%. So if I ask a question, what is the percentage of scores, right, or the proportion that makes up proportion of scores that are between the mean and 1 standard deviation below the mean? Well, that is 34.13%, just like it was on this side. But we can do more with this, right? If I ask you, what is the proportion of scores that are between the mean and negative, and a z-score of -2, or 2 standard deviations below the mean? Well, that would be 34.13% plus 13.59%, right? So we would be adding up all this right here. We would add up these two numbers. All right. If I said, oh, thanks, I'm sorry. Oh, okay, interesting. If I said, well, what percentage of scores are positively beyond the mean? Well, that's 34.13 plus 13.59 plus 2.28, which would give us 50%. Right? If you add up all three of these, they're going to give us 50%, because again, this is symmetrical, right? And so the same for this side. If we add up all of the stuff on this side, all three of those percentages, it's going to give us 50%. 50%. All right. Okay. All right. So what are the characteristics of the normal distribution? So like I said earlier, sections on the left side of the distribution have the same area as corresponding sections on the right side. And because z-scores define the sections, the proportions of area apply to any normal distribution. That's important. If it's not a normal distribution, then what we just went over does not apply. And so this is regardless of the mean, and this is regardless of the standard deviation. So let's do some kind of questions for this, right? So let's say the population distribution of SAT scores is normal with a mean of 500 and a standard deviation of 100. Given this information about the population and the known proportions for a normal distribution, we can determine the probabilities associated with specific samples. For example, what is the probability of randomly selecting an individual from the population who has an SAT score greater than 700? So that would be the probability of getting a score that is greater than 700. So to do this, we're going to follow step-by-step procedure. First, the probability question is going to be translated into a proportion question. So out of all the possible SAT scores, right, what proportion corresponds to scores greater than 700, right? And so these all the possible SAT scores tells us that we're dealing with a population distribution, right? And so the mean is 500, right? And so the score of 700 is above the mean or to the right of the mean, right? And because we're interested in all scores greater than 700, we're going to shade in the area to the right of 700. And this area represents the proportion we are trying to determine. All right, so the third part of this is to identify the exact position of the score x equals 700 by computing a z-score, right? And so we have all our necessary information. We have the raw score, right, which is 700. We have the population mean, which is 500. And we have the standard deviation, which is 100. So 200 over 100 equals a z-score of 2. So that is an SAT score that has that as a score of 700 is exactly 2 standard deviations above the mean. And that's going to correspond to a z-score of 2. All right, and so we've also located this, right? So that is an SAT score of 700 is exactly 2 standard deviations above the mean. It corresponds to a z-score of 2, right? And so finally, what is a proportion? The proportion is what we're trying to determine, right? So we change the notation. Right now we put in the z-score. What's the probability of getting a z-score that is greater than 2? Because that's equivalent to what we had before, which is what is the probability of getting an X score that is greater than 700, right? Well, if we look at our normal distribution with the z-scores, we find that the proportion would be 2.28%. Right? So we have our proportion here, right? So these are all equivalent, right? It's 2.28%. All right. Let's get rid of that. Get rid of that. So reading it in a different way, in all of the normal distributions, right? Regardless, doesn't matter, regardless the values of the standard deviation or the population mean, they're all going to have 2.28% of the scores in the tail beyond a z-score of 2 for any normal distribution, given any mean or standard deviation. This is going to apply as long as it's a normal distribution. All right. So the unit normal table. So the proportion for only a few z-scores can be shown graphically, right? We only shown about 6 of them, right? And so the complete listing of z-scores and proportions are going to be provided in the unit normal table. And this is going to be in the appendix of your book in table B1, right? And this is what this looks like, right? This is what the unit normal table looks like. And I'm going to kind of go over this, right? So in column A, we have the z-scores, right? We have z-scores going up to a z-score of, I believe, 4, all right? These are all the z-scores listed in order from 0.00 all the way to 4, right? And we are going to have the z-score is going to bisect, meaning it's going to divide, right? Or cut through the distribution wherever it lies. And when it cuts through the normal distribution, it's going to make 2 parts. One part is going to be called a body, and another part is going to be called a tail. The body is always going to be the bigger part. The tail is always going to be the smaller part. And so they have their own respective columns. So if the body, right, if the z-score is 0, right, meaning that it's the mean, right, the proportion in the body is going to be 0.50, and the tail is going to be 0.50, right? Because these have to add up to 1, right? It has to add up to 1. Right, but normally we don't have z-scores that are equal to the mean, all right? So, so in column B is going to be the proportions of the body, which is usually the bigger portion of where the z-score bisected or divided the distribution. And the portion of the tail is going to be in the C, in column C, which is going to be the smaller part of where the z-score divided the normal distribution. All right, so let's take a look at this. So let's say we had a z-score. Let's say the z-score is, 2, right? Z-score of 2, right? This z-score has bisected, right? They cut through the normal distribution. And so when it cut through the normal distribution, it created 2 parts. One part is the body. It is the bigger proportion. The other part is this one right here, which is in column C. It's the tail, which is going to be the smaller proportion. All right. And so we also have another column called column D. And column D is the proportion between the mean and a z-score. Right? What is that specific proportion between a mean and a z-score? All right. All right. So we can do a lot of things with this, and we're going to for this lecture and the next. All right. So just some kind of information about this, so we're all on the same page, right? So we use the distribution, right, to demonstrate how the unit normal table can be used to find specific proportions of a normal distribution. All right, so the figure shows a normal distribution with a vertical line that's drawn at a z-score of positive 0.25. So using the proportion of a table shown in figure 6.6, right, we're going to find the row in the column in the table that contains a z-score of 0.25 in column A. Now, reading across the row, you should find that the line drawn at z equals positive 0.25 separates the distribution into 2 sections, with the larger section containing 0.5987 or 59.87% of the distribution, and the smaller section containing 0.4013 or 40.3% of the distribution. All right. Also, there's exactly 0.0987 or 9.87% of the distribution between the z-score, between the mean and the z-score of 0.25. All right, so let's look at that. All right, so here is our z-score of 0.25, right? It is dividing this distribution into two parts. This part is the body. This part is the tail, all right? Now let's use the unit normal table to find out these percentages of these proportions, all right? So in column A, again, has z-scores. Here is the z-score of 0.25. The body, the proportion in the body is 0.5987. The proportion in the tail is 0.4013. And the proportion of the mean, between the mean and that z-score of 0.25 is 0.0987. All right. All right, so again, the body is always going to correspond to the larger part of the distribution, whether it is on the right side or the left side. Similarly, the tail is always the smaller section, whether it is on the right or the left. It doesn't matter. The tail is always a smaller proportion. The body is always a larger proportion. And so again, well, not again, but because the normal distribution is symmetrical, the proportions on the right side are exactly the same as the corresponding proportions on the left side. So, for example, we use the unit normal table to obtain proportions for z equals positive 0.25. But we also are I'm going to show you the same proportions for a z equals negative 0.25. So for a negative z-score, notice that the tail of the distribution is on the left side and the body is on the right side. For a positive z-score, the positions are going to be reversed. However, the proportions are going to be exactly the same. With whatever the body is, doesn't matter what side, whatever the body is going to be 0.55987, and the tail is 0.4013. And so the table, our unit normal table, does not list negative z-scores. So in order to solve problems with negative z-scores, you must look at the positive value of the z-score and understand that what you are looking for is a negative z-score, all right? And so the third kind of important thing is that although the z-score values change signs from positive to negative, right, and from one side to the other, the proportions are always positive, right? Because the proportions added up have to, equal 1. There are no negative proportions, right? So column C in the table always lists the proportion in the tail, whether it is in the right-hand tail or the left-hand tail. So let's look at that negative z-score, right? So in this one, I have a z-score of negative 0.25. And so this separates the normal distribution right here. And it creates, again, two parts, this part and this part. Well, this part is the larger part. It is the body found in column B. This part is the smaller part. So this is the tail. And this is going to be found in column C. All right. But as you notice, the proportions are still the same. The tail in this reverse is 0.4013, and the tail on the other side is 0.4013. And the body is the same proportion as well. All right. That's because the normal distribution is symmetrical. Okay. Um, so the probability and proportion and z-scores. So the unit normal table lists relationships between the z-score locations and the proportions in a normal distribution. So if you know the z-score, you can look up the corresponding proportion. If you know the proportion, you can use the table to find the z-score. Probability is going to be equal or equivalent to proportion. All right. So we're going to go over some problems using this unit normal table, and I'm going to utilize the full table in a second. All right. So for all of these, I'm going to give you steps on how to do them. And then towards the end, I'm going to give you a sort of a cheat sheet, which tells you what you should be doing next, given how the question is worded. So, and this one is when given a z-score and you're asked to find a proportion, right? So they give you a z-score and you're asked to find a proportion. Your first step, and this is going to be the first step for all of these, is that you're going to sketch the distribution, right? You're going to draw a distribution, right? And you're going to shade in the area that you are trying to find. And you're going to ask yourself 2 questions for this particular kind of question. Is the z-score to the left or to the right of the mean? And second, are we looking for a body or a tail? Step 2 is to look up the z-score and find the correct column with the proportion. All right. All right. So those are the 2 steps, right? So in this one, it asks, what proportion of the normal distribution corresponds to a z-score value greater than z equals 1, right? So written as a proportion, p equals z, a z-score of greater than 1, right? So first you would sketch the distribution. So we've sketched it right here. This is a distribution, right? And you want to shade in the area you're trying to find. Well, z-score of 1 is right here. And we're trying to find all of the proportion of z-scores that are greater than 1. So we are interested in this part right here. All right. And so to find this shaded area, you simply look for the z-score of 1 in column A to find the appropriate row in the unit normal table. Then you're going to scan across the row to column C to find the proportion. All right. And you should find the answer is 0.1587. So let's do that. All right. So I'm going to pull up the actual unit normal table. And this is in your modules for chapter 6 and for chapter 7, where we're going to still be using the unit normal table. All right. So you have that. And it's also in the back of your textbook. All right. So let's stop this share. I'm going to make sure you can see this. Okay. Yikes. Give me a second. Sorry, give me a second. Messed up somewhere. Okay. One second. Okay. Having some computer issues. Okay, let's see if we can't do it now. Here's a Zoom meeting. I'm going to share my screen. Okay. Okay, so right now you should be able to see the unit normal table. All right. Um, let's. So in the question that we were working on, right? Um, it was, hey, what is the proportion? Oh, I can't write on this. Okay, what is the proportion? I see. What is the proportion of z-scores that are greater than 1, right? So we're going to find our z-score in column A, right? So it starts at 0.00. So we're going to go all the way down until we get to a z-score of 1. So here's a z-score of 1, right? And we were looking for a tail, right? So we're going to scan across to column C, which is the proportions in the tail. And we find that for a z-score of 1, the body proportion is 0.8413, and the tail proportion is 0.1587. All right. All right. Okay. So let's try another question, right? Oh, let's see. And let's keep it like this. Okay. All right. So the next question. So for a normal distribution, what is the probability of selecting a z-score that is less than 1.5? So that's in the symbols, this is how this would look, right? 1.5. Right, so our goal is to determine the proportion of the normal distribution that corresponds to z-scores less than 1.5. A normal distribution shown right here, right, has a z-score of 1.5, right? So the z-score of 1.5 is right here, right? And this is the proportion we're trying to find. Clearly, the shaded portion is more than 50%, so it corresponds to the body of the distribution, right? So saying, hey, it's saying, what is the probability of finding a z-score that is less than 1.5? So less than. So that's all of this right here, right? So this z-score is going to make two parts. One is the body, which is this side, and one is the tail, which is this side. We are looking for a body. We are looking for a body, right? So we would go to our unit normal table and look up the z-score of 1.50. All right, let's find that. So a z-score, so in column A, we're looking at the z-scores, and a z-score of 1.50 is right here. And we are looking for a body, so we're going to look for the corresponding proportion in column B, and that gives us 0.9332. All right, 0.9332. Or 93.32% of the scores are going to have a z-score less than 1.50. All right. So a different problem. So many problems require that you find proportions for negative scores. So for example, what proportion of the normal distribution is contained in the tail beyond z equals negative 0.50, right? So here we drew the distribution, right? And we put where the z-score is at, negative 0.5, right? And again, the z-score is going to create it's going to separate the distribution into two parts. One is going to be a body part, the other one's going to be a tail. You need to know if you're looking for a body or a tail. Well, we're looking for all of the z-scores, right, that are less than negative 0.5. So we're going this way. So we're looking for all of this right here. Well, this is a tail, right? Because this is the smaller part, whereas this part is the body. So we're looking for a tail. So then we go to our unit normal table, right? But this time, when we go to our unit normal table, we realize that we do not have any negative z-scores. So we have to use the positive version of that z-score. So the z-score we were looking for was negative 1.50. So in this case, we're going to look for a positive 1.50. Oh, I'm sorry, negative 0.5 is the z-score we're looking for. Negative, so we're looking for a positive 0.5. Give me a second. Oh, sorry, positive 0.5, yes. All right, and so a positive 0.5 z-score is right here. And we are looking for a tail. So we're looking for the corresponding proportion in column C, which has the listing of tails. So that is 0.3085, right? 0.3085. Or 30.85%. All right. All right, so we can do other kinds of questions with this. So now, given a proportion or a percentage, find the z-score. So now the last question was saying, hey, here's a z-score. What is the proportion or percentage? Now it's asking us, hey, we're going to give you the proportion or percentage. Tell us where the z-score is at. So in this one, the first step is essentially the same, right? We're going to sketch the normal distribution and draw a vertical line that separates the two parts. And then we're going to shade in the part that you want to find. And we're going to ask ourselves, is the shaded part that we need to look for, is it below the mean or above the mean? All right. We're going to also look up that proportion in the table and find the z-score for that proportion, and find out lastly if the z-score is negative or positive, right? Because our normal distribution doesn't give us that. Our unit normal table doesn't give us that. So let's look at some examples of this, right? Let's see. So for a normal distribution, right, what z-scores separates the top 10% from the remainder of the distribution? Right, to answer this question, we have sketched a normal distribution, right? This is this one right here. And drawn a vertical line that separates the highest 10% approximately from the rest, right? So this line right here. It separates the top 10% from the bottom 90%. The problem is to find the exact location of this line. And so for this distribution, we know that the tail contains 0.100 or 10%, and the body contains 0.900. So to find the z-score value, you simply locate the row in the unit normal table that has either 0.1000 in column C or has 0.900 in column B. All right. So for example, you can scan down the values in column C until you find a proportion of 0.100. Note, right, this is very important, that you probably will not find the exact proportion, but you can use the closest value listed in the table. So for this example, the proportion of 0.100 is not listed in column C, but you can use the closest one to it, which is 0.1003, which is listed. All right. And then once you found the correct proportion in the table, you simply read across the row to find the corresponding z-score value in column A. All right. So let's do this. All right. Let's get it. Yes. Okay. All right. So the question asks, right? So we're going to look in column C, right? The proportion of the tail for a proportion that's closest to 0.100, or the equivalent of 10%. So if we go down in column C, we're going to keep going down, right? The closest number right here to column to 0.1000 is 0.1003. And then if we look over, because our question is asking us, what is the z-score, right? So the z-score is 1.28, right? So, but we got to be careful at this point, because the table does not differentiate between the right-hand tail and the left-hand tail, all right, of the distribution. Specifically, the final answer could be either a z-score of negative 1.28 or a z-score of positive 1.28, all right? So for this problem, you would have to look back at your distribution and figure out if this is a positive z-score, meaning it is above the mean, or if this is a negative z-score, meaning that it is below the mean. In this case, it is a z-score that is above the mean. So the z-score is 1.28, positive 1.28. Okay. So now, let's say the question is giving you the proportion, and the question discusses anything that has the term middle in it. If it has the term middle in it, you're going to do something similar to this, all right? And it asks you to find the z-scores. So, excuse me. So finding a z-score location that corresponds to different proportions, and the question discusses middle. The first step is you're going to sketch the distribution and draw a vertical lines, I should say. You're going to shade in the part that you want to find. Then you're going to divide the percentage or proportion of the middle evenly between the mean. Then you're going to find the two proportions in column D. Then you're going to read across to find the z-score for the negative and positive side of the z-score. All right, so let's see how that goes. All right, so here's a question set up. All right, for a normal distribution, what z-score values from the what z-score values form boundaries that separate the middle 60% of the distribution from the rest of the scores? So again, first thing, we're going to draw the distribution. Here is it drawn, right? And so we sketch the normal distribution, and we're going to draw a vertical line so that roughly 60% of the distribution in the central section, with the remainder split equally between the two tails. So we draw a line where that's going to cover about 60% of the middle of this distribution, which is what we did right here, right? So the problem is to find the z-score values and to find the exact locations for those lines. And so to find the z-score values, we begin with the known proportion. The proportion is 0.60, right, in the center. And the 0.40 is divided equally between the two tails. Although these proportions can be used in several different ways, this example provides an opportunity to demonstrate how column D in the table can be used to solve problems, right? So for this problem, 0.60 in the center can be divided in half, right? We can divide this in half. Here's the mean, right? 30% of this is on this side of the mean, and the other 30% is on the other side of the mean, or 0.30. All right. And so what we would do is we're going to go to column D and look up the proportion that is closest to 0.3000, or 30%, right? And so let's look that up. Let's go to the table and see what that is. So now we are in column D, and we're looking for the number that is closest to 0.300. All right. So the number that is going to be closest to 0.300 is right here. That is 0.2995. All right. And 0.2995 corresponds to a z-score of 0.84. All right. However, in this question, right, it is asking us for two z-scores, one on the left side, one on the right side, right? So the one on the left side is going to be negative 0, a z-score of negative 0.84. And the one on the right side is going to be a z-score of positive 0.84. All right. Okay. And so that's how you would do a question that in that kind of way that has to deal with the middle proportions. All right, so let's go to a lesson check so we can do some of these from scratch. All right, so for the first one, it says find a proportion of a normal distribution that corresponds to each of the following sections. So we have to find a proportion. They're giving us z-scores, right? They want us to find a proportion. So the first thing we're going to do is we are going to draw our distribution. All right, and here is the mean, right? And then we're going to approximate where our z-score is at, right? So we can know if we're looking for a body or a tail, right? So in this question, it asks, what is the proportion of z-scores that are less than 0.25, right? Well, a z-score of 0.25 is above the mean. So but it's really close to the mean. It's somewhere right over here, right? And it's asking us, what are the proportion of z-scores that are less than 0.25, right? So 0.25 is here. And it wants us to find everything that's less than that, right? So the z-score divided the normal distribution into two parts. One is going to be a body and one's going to be a tail. Well, this is obviously a body because it's bigger than its other side, which is the tail, right? So we're looking in for a proportion in column B, right? So how do we do that? How do we go about doing that using our z table? So we're going to find where the z-score of 0.25 is, which is right here. And then we're going to find the body, the proportion in the body, which is 0.5987. All right. So let's do another problem with that one. Let's see. So the next one asks, hey, what is the proportion of z-scores that are greater than 0.80? Well, you know what? Let's do another. Let's not do that one. All right. So let's do C. What is C is asking, what is the proportion? Right. What is the proportion of z-scores that are less than negative 1.50? Right. So we know that our z-score is below the mean because it's a negative z-score. And so our z-score is approximately somewhere around here, right? A z-score of negative 1.50. And it's asking us, what are all the z-scores that are less than that particular z-score? So it's all the z-scores that are over here, right? It's this small part right here. So is this a body or a tail? Well, this is a tail, right? So what we're going to do is we're going to find the z-score in column A and then look over to the proportion that is in column C, which tells us the proportion that makes up the tail for that particular z-score. So let's go to it, right? But that z-score was negative, right? And so there are no negative z-scores in this unit normal table. So we'll have to look for the positive z-score. So the positive z-score 1.50. All right, let's look for that. So here is the z-score of positive 1.50. We're going to go to column C, all right, to find the proportion in the tail, which is 0.0668, right? Or 6.7%, all right? Okay, so let's do a different question, right? So for a normal distribution, for number 2, find the z-score location that divides the distribution as follows. The first one separates the top 20%. So this one is starting you off with either proportion or percentage, and they're asking you to find the corresponding z-score, right? So in this one, the first thing we're going to do is we're going to draw the distribution, right? Put our mean, right? And this one asks, hey, separate the top 20% from the rest. What is the z-score that does that? Well, the top 20% is going to be above the mean, right? So it's somewhere over here. This is an approximation, right? That's this 20% or 20% or 0.2000, right? It's 20 that's 20%, and 0.20 is the proportion, right? So in this one, let's see. So we're going to look, the 20% is this small part right here, right? It's that tail, right? So this is the tail. So what we're going to do is we're going to go into column C, right, in our unit normal table, and find the closest proportion to 0.2000. So let's do that. All right, so now we're in column C, and we're going to find the number that is closest to 0.200. Okay, so in column C right here, we're going down 2, 2, 2, 2. So the number that is closest to 0.2000 is 0.2005. And so then we're going to, because the question asks us, what is the z-score? So we're going to look over and find the z-score. That z-score is 0.84. All right, but remember, we have to make sure that z-score, whether the z-score is positive or negative. Well, in this case, that z-score is above the mean. So it is a positive z-score. So it would be a z-score equals positive 0.84. All right. So let's say we're doing the middle, separate the middle 70% from the rest. Well, for this one, right, we are first going to draw our distribution. We're going to put our mean, right, in the middle. And this one asking us, hey, the middle 70%, right? So the middle 70%, what separates the middle 70% from the rest? So here is our middle 70%. All right, that makes up 70% of this distribution, right? So for these questions, right, we're going to use column D. And the way we're going to use column D is we're going to divide this 70% by 2. So there's 35% on this end. There's 35% below the mean, and it's 35% above the mean. 35% plus 35% gives us 70%. So we're going to go into column D of our unit normal table and find the closest number to 0.3500, right? 0.3500, which is equivalent to 35%. All right, so let's go to our unit normal table. We're going to look into column D and find the closest number to 0.3500. All right, so if we're looking down here, right, we're looking at threes, proportion in column D. The number that is closest to 0.3500 is 0.3508, which corresponds to a z-score, which is what they're asking you, of 1.04. So we have two z-scores, right, that form the boundaries. The one that is below the mean is negative 1.04. The one that is above the mean is positive 1.04. All right. Okay. Give me a second. This is erase all that. Oh, wait. So question 3. The tail will be on the right hand side of a normal distribution for any positive z-score. Is that true or false? That is going to be true. All right. And so here is the answers to these questions. All right. And we are going to skip over these because we've kind of done those questions already. All right, so well, let's do this one. So decide if each of the following statements are true or false. Any negative z-score, the tail will be on the right-hand side, right? So we can try this out, right? So let's draw a distribution. Here's the mean. If we have a negative z-score that we're looking for, it's below the mean, right? So let's do here, right? Well, it's separating this into two parts. This part is going to be a tail, and this part is going to be a body. So the tail, so for this question, that's going to be false, right? For any negative z-score, the tail is going to be on the right-hand side. And also for any positive z-score, the tail is going to be on the left-hand side. So you can just kind of draw that out to figure that one out. All right. Okay. So probabilities and proportions for normally distributed scores. So the probabilities given in the unit normal table are only going to be, accurate for normally distributed scores. So the shape of the distribution should be verified before you use it. It has to be a normal distribution. So now for normally distributed scores, what we're going to do to answer some of these questions, we're going to transform the x-score values into z-scores. Then we're going to look up the proportions corresponding to the z-score values. So our first kind of question is, so they're going to give us raw scores in a normal distribution. They're going to give us raw scores, and they're asking us to find out what the probability or proportion is. So finding a probability or proportion when raw scores, a standard deviation, and a population mean is given. So the first thing you're going to do, it's always the first step. You're going to sketch the distribution and draw a line where the score is at. Second, you're going to change the x value into a z-score. Third, you're going to look up the z-score in the unit normal table. And then finally, you're going to find the correct column for the proportion. So let's see a question for that one, right? So it is known that IQ scores form a normal distribution with a population mean of 100 and a standard deviation of 15. So given this information, what is the probability of randomly selecting an individual with an IQ score that is less than 120? All right. So the first step, right, is after we have drawn this out, all right, which is shown below, the first step is to change the x value into a z-score. All right, and so we put in all the information. Here's our z-score formula, and so the raw score is 120. The population mean is 100, and the standard deviation is 15. And if we simplify that, it becomes a z-score of positive 1.33. So an IQ score of 120 corresponds to a z-score of 1.33. All right. And IQ scores less than 120 correspond to z-scores that are less than 1.33. So the next step is we're going to look up the z-score value in the unit normal table, because we want the proportion of the distribution in the body to the left of x equals 120, right? Because they ask, what scores are less than 120? So instead in z-scores, what proportion are scores that are, what proportion of z-scores are less than 1.33? Well, 1.33 is above the mean, right? And so we're looking for this whole shaded part here, all right? And so we are going to look in our unit normal table, and we are going to look for the z-score of 1.33. And then because we're looking for the body, we're going to look across into column B to find the proportion in the body. So let's do that. So we're looking in column A for the z-score of 1.33. So let's just find z-score of 1.33 in column A. And here is the z-score of 1.33 right here. And we're going to look across into column B for the body, which is 0.9082 or 90.82%. All right. Okay, and so that's how you would do that particular kind of question. All right, so now let's say we are given 2 raw scores and asked to find the probability, right? So this one, we're going to find a probability when 2 raw scores are given. The first step is to sketch the distribution and draw a line where the score is at. Then we're going to change the 2 x values into 2 z-scores. Then we're going to look up those z-scores, and then we're going to use the correct columns to find the proportions. And then we're either going to add or subtract the 2 proportions depending on the type of question that we have. So let's go through an example. All right, so the example, the highway department conducted a study measuring driving speeds on a local section of interstate highway. They found an average speed of 58 miles per hour with a standard deviation of 10. The distribution was approximately normal. That's important. So we're dealing with a normal distribution. Because if we're not dealing with a normal distribution, then we cannot use the unit normal table. Given this information, what proportion of the cars are traveling between 55 and 65 miles per hour? So using the notation, right? The probability um, of, of being between 55 and 65 miles per hour. All right. So what we did was we took those two X scores and we are going to change them into Z scores, right? As shown below. So a 55 miles per hour is equivalent to a Z score of negative 0.30. And a miles per hour of 65 is equivalent to a Z score of 0.70. And we're going to draw our distribution, right? So the mean is 58. So our score of 55 is below the mean. And our score of 65 is above the mean, right? So that's going to be that's the positive Z score. All right. Then we are going to look up those two, all right, those two Z scores. All right, so let's continue with this question. Give me a second. Okay. So in this one, we see that the proportion we are seeking can be divided into two sections. One is the left area of the mean, and two is the area right of the mean. So the first area is the proportion between the mean and negative 0.30. And the second is the proportion between the mean and positive 0.70. And so for this, we're going to use column D of the unit normal table. And these two proportions are going to end up being 0.1179 and 0.2580. And the total proportion is attained by adding these two sections, right? And so that would give us 0.3759. So let's look up those proportions in column D. So the Z score, right, was negative 0.30, right? But there are no negative Z scores in the unit normal table. So we're looking up Z score of positive 0.30. So where is that at? Let's look up here. Z score of positive 0.30, right? The proportion is going to be 0.1179. All right, that's the first proportion. The second proportion is going to be in column D with the Z score of 0.70. So let's look at column A for a Z score of 0.70. All right, and so that is right here. And so we're looking in column D, and in column D, that proportion is going to be 0.2580, right? And then we're going to again add those two proportions up, and that gives us a proportion of, I believe it was 0.3759. Yeah. All right. And that would be the answer to your question. All right. And so now to make this a little bit easier, right? We've kind of been doing this, but I'm going to give you, this is essentially the cheat sheet to always know what you're going to do next with these, right? So if you start off with a proportion in the question or a probability, and they ask you to find the raw scores, right? You are going to first use the unit normal table to find the Z score, right? And then you're going to use the Z score formula, more specifically the X score formula, right? To find out what the original raw score was. But if they ask you, given a raw score, find out what that proportion or probability is, Well, you're going to follow this triangle, right? You're going to go from, you're first going to change an X score into a Z score, and then you're going to use the unit normal table to find the proportion or the probability. All right. And what we've been doing beforehand, we've been going from, I've been giving you a proportion and then asking you to find the Z score, right? Or a Z score and find the proportion. Or we've been talking about here, given a raw score, find the Z score, or Z score, find the raw score, right? Which we kind of did last week. All right. What you can't do, though, and this is why it is dashed, right? You can't go from a raw score to a proportion. You have to follow those steps, and you can't go from a proportion to an X score. You have to follow these steps right here. All right. So that's your cheat sheet. All right. On how to do a lot of these questions, or all the questions essentially. Okay. So let's do some of those questions where we go through the whole thing. So given a proportion, how to find a raw score, right? So the problems when starting with a proportion and you are trying to find a raw score. So the first step is draw the distribution with all of the information that you have. Next step is to find the Z-scores that correspond to the proportions. Step 2, determine whether the Z-scores are positive or negative. Step 3, transform the Z-scores into X values by putting it into the X formula, right? And that's that formula where it's the mean plus the Z-score times the standard deviation. So let's look at an example of this. So in this one, the US Census Bureau reports that Americans spend an average of 24.3 minutes commuting to work each day, assuming that the distribution of commuting times is normal with a standard deviation of 10 minutes, right? So it's a normal distribution, right? So if it wasn't a normal distribution, we would not be able to use the unit normal table. How much time, right, do you have to spend commuting each day to be in the highest 10% nationwide? An alternative form of the same question is presented, well, let's not read that. The distribution is shown in figure 6.14 with a proportion representing approximately 10% shaded in the right-hand tail. So in this problem, we begin with a proportion, so 10% or 0.10, and we are looking for a raw score. According to the map in figure 6.13, we can move from the proportion to the X scores via Z scores, right? This is what this was saying right here. You go from proportions to the Z score to the X score. All right. All right, so the first step is to use the unit normal table to find the Z-score that corresponds to a proportion of 10% or 0.10 in the tail. First, scan the values in column C to locate the row that has a proportion of 0.10 in the tail of the distribution. So again, you're not going to find exactly 1.000, but the closest value to it is going to be 0.1003. And then you're going to read across to find what the Z-score is. That Z-score is 1.28. All right. And then you're going to change that Z-score into a raw score. All right. By putting it into the X formula, right? So X equals the population mean plus the Z-score times the standard deviation, right? So the population mean was 24.3. The Z-score was 1.28 times the standard deviation, which was 10. And so you add all that up and that gives you 37.1. So the answer for our original question is that you must commute at least 37.1 minutes a day to be in the top 10% of American commuters. All right. So now the question becomes, so given a proportion in the middle, so here's that word middle again, right? And you are trying to find raw scores. So problems when starting with a proportion in the middle and you are trying to find raw scores. So first thing you're going to do is you're going to draw the distribution with all of the information. Then you're going to find the z-scores that correspond to the proportion for each one in column D. Then you're going to determine whether the z-scores are positive or negative. And then third, you're going to transform the z-scores into x values by putting it into the x formula, right? All right, so let's see an example of this. So again, we're going to use that same distribution. Again, the distribution of commuting time for American workers is normal with a mean of 24.3 minutes and a standard deviation of 10. For this example, we find the range of values that defines the middle 90% of the distribution. The entire distribution is shown in this figure below with the middle portion shaded in. So the 90% is 0.9000 in the middle of the distribution can be split in half with 45% or 0.4500 on each side of the mean. Looking up 0.500 in column D of the unit normal table, you will find that the exact proportion is not listed. However, you will find that the closest to it in column D is 0.4495 and 0.4505. Both of those are equally close. So technically, either value is acceptable, but we're going to use the value of 0.4505 so that the total area in the middle is at least 90%. All right. And so reading across the row, you should find that the z-score is going to be 1.65 in column A. So the z-score at the right boundary is z equals positive 1.65, and z-score at the left boundary is going to be negative 1.65, right? These are right here, right? So in either case, a z-score of 1.65 indicates a location that is 1.65 standard deviations away from the mean. For the distribution of commuting times, one standard deviation is 10. All right. So if we put both of those into our x formula, right? So x equals the population mean plus the z-score times the standard deviation, right? The first one, right? We are, let's see, what is the population mean? What is that at? Okay, yeah, population. Okay, so for the first one, 24.3 is the population mean, right? Plus the z-score of 1.65 times the standard deviation of 10. All right, and that's going to give you 16.5. But that's only for the positive z-score. But the negative z-score is 24.3 minus 1.65 times 10, which is going to give you, well, that's not 16.5. That's 40.8. And for this negative z-score one, it's going to give us, you add this all up, it's going to give us 7.8. So our two raw scores are 40.8 and 7.8. I do it this way because the way that they try to explain it to you in the book is sort of convoluted. By putting it into the formula right away, it becomes clear how to go about doing the math associated with this particular formula. Okay. Okay. Let's see. All right. So let's do some of these problems, right? So we can kind of see this in real time, how to go about doing these. All right. So for this first one, right, for a normal distribution, right, with a mean of 60 and a standard deviation of 12, find each probability value requested. So we're starting with some kind of raw score, and they want us to find a probability. So let's start with the probability of an X score being greater than 66, right? So here's our distribution. We're going to put our mean, right? And our population mean is 60, right? And our standard deviation is 12, right? And so the score is 66. So 66 is above the mean, right? So somewhere right here. And the question is asking us, what is the probability of finding and getting an X score that is greater than 66? So we're looking for all this right there. We're looking for a score that is looking for all the proportion of scores that are greater than 66. So this is going to be a tail, right? A tail, right? So now, in order to get to that, right, we are going to have to find the z-score, right? And then find the proportion in the correct column, right? So we have 66, right? So now we are going to remember this cheat sheet. Let's go back to that. So we started with an X score, right? And we want to find a proportion. So we're going to use the z-score formula to turn the X score into a z-score, and then find the proportion in our unit normal table. All right. So let's put it into our z-score formula. Z equals the X score minus the population mean over the standard deviation, right? And so the z-score equals 66, right? I'm sorry, not the z-score, but the raw score is 66 minus the population mean of 60 divided by 12. So that's going to give us 6 over 12. All right. And if we use our trusty calculator, right? Always use your calculator. Don't want to do this stuff in your head, even though if it seems easy. 6 divided by 12 is going to give us 0.5. So it's a z-score of 0.5, right? So now we are going to go into our unit normal table and look up where the z-score of 0.5 corresponds to the proportion in the tail in column C. All right, so let's go to a z-score of 0.5. All right, let's see where that's at. So here's a z-score of 0.5, right? And we are going to go to column C because we're looking for the proportion in the tail. And so that gives us 0.3085 or 30.85%. All right, that's the answer for that first question. All right, so let's do a more difficult one. Okay, so let's do D, right? So D is, hey, what is the probability of uh, of scores between 48 and 72, right? So for this one, right? Let's see. Let's first draw our distribution, right? So our population mean is 60, right? And our standard deviation again is 12. And so 48 is below the mean, right? So that all off the bat, that's one of those is going to be a negative z-score, right? So here's 48, and 72 is above the mean. So that is above the mean. So we're trying to find all of the stuff right in here, all right? So what we are going to do is first we are going to change those raw scores into z-scores. So the z-score for the first one is going to be 48 minus 60 over 12. And that gives us negative 12 over 12, which gives us negative 1. So the first one is a z-score of negative 1. For the second one, the raw score of 72, this is going to be 72 minus 60 over 12, which gives us 12 over 12. And that gives us a z-score of positive 1. All right. So then the next step of this, right, is we're going to try to look for the probability. So the probability, right, is going to be, we're going to use column D, right, to find the sections of these on either side of the mean. So we're going to look up our z-score of 1 and then go to column D and find out what the proportion of those are. So let's take a look. All right, so here is our z-score of 1. We're going to go to column D. All right, and for the proportion between the mean and the z-score of 1 is 0.3413. So for this question, we are going to add 34.13 plus 34.13, and that is going to give us I'm sorry, 0.3413. Let's see. 0.3413 and 0.3413, that's going to give us 0.6826 or 68.26%. All right. So that's how you would do those particular questions. All right. Let's see. Okay. So the next question, scores on the mathematics section of the SAT reasoning test form a normal distribution, right? It's normal, right? So we know we can use a unit normal table with a mean of 500 and a standard deviation of 100, right? So if the state, if the college only accepts students who score in the top 60% of this test, what is the minimum score needed for admission? So this one, right, is starting with a proportion, right? And it wants us to find out a raw score, right? So let's draw our distribution, all right? And so the top 60%, so think about it this way. If this is the top 60%, right? And a normal distribution, the mean cuts it in half. Well, that means that the top 60%, right? that score is somewhere over here, a little bit below the mean, right? This represents the top 60%. We're trying to find all of this right here, all right? Top 60%. And so again, we're going to draw the distribution with all of the information. Then we're going to find the z-score that corresponds to that particular proportion. So we're looking for a body, right? Because this is the larger part, right? We're looking for a body. And so we're going to go to our unit normal table and find where 0.60 in the body, the number that's closest to 0.6000. So let's see if we can't find that. So the number that is closest to 0.600 in the body is 0.5987. All right. So 0.5987, which corresponds to a z-score of 0.25, right? However, don't make that mistake. This z-score is negative because it is below the mean. So it's a negative. So it's a z-score of negative 0.25. All right. But our question ultimately asks, what is the minimum score needed? So we need to change that z-score into an x score, right? And so we are going, all right, we are going to put that into our x score equation. So x equals the population mean plus the z-score times the standard deviation, all right? And so our let's see, our population mean is 500 plus our z-score of let's just put negative plus negative 0.25 times standard deviation of 100. All right. And if we add all of that up, all right, that is going to give us x equals 475. All right. Give me 1 second. Right. All right. So that gives us 475, right? So that would be the answer to question A. You need a score, but the minimum score of at least 475 for admission into this particular state college. All right. We won't do B because that is essentially the same kind of question, but let us do question C. All right, question C. I mean, number 2C, I should say. 2C. Okay. All right, so what scores form the boundaries for the middle 50% of the distribution? Oh, thanks. Okay. So let's draw the distribution again, right? And now it just wants us to find what the scores form the boundaries for the middle 50%. Right, so the middle 50% is here and here, and we're trying to ask middle 50% of this. Well, you know that when you're dealing with middle, that you're going to ultimately be using column D, and that you're going to have to break apart this middle, right, into two separate and equal parts. So there's a 25% on this part that's above the mean, and 25% on the other part that's below the mean. All right, so you are going to go to column D, right, and find the proportion that is closest to 0.2500. All right, so let's do that. Let's go to our Z table. Let's go to column D and find the proportion that is closest to 0.2500. 0.2500, 0.2500. Okay, so we have two numbers. They're relatively close, but the closest one, right, to 2.500 is going to be 0.2486. And that's going to correspond to a z-score of 0.67. So the two z-scores on here is negative 0.67. That's below the mean, and positive 0.67, which is above the mean. All right, so next thing is that we are going to find the raw score by putting both of those z-scores into our X formula. Remember the X formula? So X equals the population mean plus the z-score times the standard deviation. All right, so let's find them. So X equals 500 plus, what was the, I had to write it down. What was the z-score that we found? Let's see, what is that again? Looking for 0.25%. What was it? Oh, it was what, 0.67? Yeah. It was 0.67. All right. So plus so 0.67 times the standard deviation of 100. All right, and that's going to give you 567. And on the other side, it's X equals 500 minus 0.67 times 100. And that's going to give you 433. All right, so there's two scores that form the boundaries of the middle 50% of this distribution. Is going to be 567 and 433. All right, so the third question asks, what is the probability of selecting a score greater than 45 from a positively skewed distribution with a population mean of 40 and a standard deviation of 10? All right, well, this one, we cannot answer this. Why? Because it is a positively skewed distribution. The unit normal table only helps us define proportions and probabilities and z-scores for a distribution that is normal. It's a normal distribution. All right. So we would not be able to do that particular question. We can't obtain the answer to that. Okay. And here are the answers to the questions. I didn't go over all of them, but I went over the ones that are the most difficult and the ones that are repeated. So yeah, we're going to skip these as we've kind of done these questions. Skip that. Okay, so looking ahead to inferential statistics. So many research situations begin with a population that forms a normal distribution. And a random sample is going to be selected, and they're going to receive a treatment to evaluate the treatment itself, right? Probability is used to decide whether the treated sample, again, is noticeably different from the population. So let's see. So the population, right, is normal, right? Let's say the population is normal. Let's say we're dealing with those, the rats given growth hormone again. Population is normal, right? With a population mean of 400 and a standard deviation of 20. All right, and we're going to take a sample from that population, and then we're going to treat it with some kind of growth hormone. And we're going to look at the treated sample and compare it, right, to the population that it came from, right? And if we find something that, is extreme, or that's far away, a sample that's really, really far away from what the population mean is, we're going to say that the scores are very unlikely. So let's look at this a different way. In a research study, right, we are going to say that the middle 95% of the distribution are high probability values, right? And so to get the middle 95%, right, it would be 95% divided by 2, which gives us 47.5%. If we're looking up a proportion, it would be 0.4750, which we would find in column D, right? So let's look that up. Oh, it erased it? Oh. So we're looking up 0.750 in column D, right? So if we look at column D, 0.4750. Let's see, 0.4750. 0.4750. All right, so 0.4750 is right here. And that corresponds to a z-score of 1.96. And if you remember the last chapter, right, we said anything that was a z-score of 2 or higher was an extreme score. Now we're being a little bit more specific using the z-scores, right? We're going to say that, hey, if we have, we're saying the middle 95% of scores are going to represent very highly probable values that we should be able to get, because the scores are relatively near to the population mean of 400. And that's going to indicate to us that if we find something that is in the middle 95%, that the treatment doesn't have any kind of effect. It doesn't work. All right, it doesn't do anything. However, the 5%, right, 2.5% on this end and 2.5% on the other tail, right? These are making up 2 tails, right? Which if you add those up, it comes up to 5%. The 5% that is outside of that middle 95%, well, they start at a z-score of negative 1.96 and positive 1.96. And we're going to say any scores that are beyond that, right, are very unlikely to be obtained from the original population. And we're going to say, therefore, that's going to provide evidence that the treatment is effective. The treatment does work. All right. And so that's one way that when we do studies, we are going to evaluate if a treatment works or not. And we're going to go more into that in our next chapter. All right. And so I want to thank you for sticking around. This chapter is very, very important in understanding probability. And so if you have any questions, please do not hesitate to ask. All right. I'm always here to help. You can always come and talk with me during my office hours. We can set up a Zoom call. All right. Or you can ask me a question on Canvas, or ask me a question via email. And y'all have a great day.